In the previous class, we were discussing about differential rate equation. So, differential rate equation dr by dt is equal to K into molar concentration of R. So, differential rate equation says that the rate of the reaction depends on the molar concentration of the reactant, and the quantitative way of expressing the dependence of the molar concentration of a particular reaction on the rate of the reaction is what we call order of the reaction. So, order of the reaction will tell you to what extent the increase in the molar concentration of a particular reactant will increase the rate of the reaction. So, the power of the molar concentration terms of the reactants together, sum of the powers of the molar concentration of the reactants are what we call the order of the reaction. So, order of the reaction is very important. In order to determine the order of the reaction, we need to have experimental data on the rate of the reaction. So, before adding a particular reactant, increasing the molar concentration of a particular reactant, you need to know what is the rate of the reaction. Once you increase the molar concentration of the reaction, either it is doubled or tripled or made it 4 times, you need to know what is the change in rate of the reaction. Then only you can predict what is the order of the reaction. That also, the rate what you are going to predict is not the average rate, it is the instantaneous rate. And also, if you wanted to determine the order of the reaction, you need to have all the experimental data in your hand. You need to plot a graph. If you connect all this experimental data about the rate of the reaction with respect to time, you will get a graph with a positive slope or negative slope. That graph represents the average rate of the reaction, and if you wanted to find out the instantaneous rate of the reaction at a particular point, you need to draw at the curve, you need to draw a tangent and you have to find out the slope. This is a Herculean task. So you need to have some shortcut method so that you can predict the extent of the reaction within a single shot. So for that only, they have introduced integrated rate equation. Integrated rate equation. As far as the integrated rate equation is concerned, it is very important with respect to the university board exam and also any other exam you are going to appear. So let's talk about the integrated rate equation for first order reaction. Let's consider a first order reaction where reactant is getting converted to product. So when you are writing down the differential rate equation for this reaction, rate is equal to dr by dt minus is equal to K into first power of the molar concentration of the reactant. And if you rewrite this equation, because we have to integrate the equation in order to get easy integration, so we'll write like this: minus dr by r is equal to K dt. We can take it like this, that dr by r is equal to change in molar concentration of the reactant divided molar concentration of the reactant is equal to minus K dt. If you are integrating this equation, you will get, by integration, you will get ln r is equal to minus of kt plus I. and this I is what we call integration constant or the constant of integration. Now you have got a small task. What is that? Is you need to find out what is the value of I. Then only this equation will become meaningful. So in order to find out the value of I, what we are going to do, we are going to consider a situation when T is equal to 0, the molar concentration of the reactant is supposed to be 0.
Supposed to be R naught.
And we'll implement this situation in the first equation, that is ln R naught is equal to minus k into when T is equal to 0 plus I. So that you will get I is equal to ln R naught. So please understand, I is the constant of integration. We have to determine the value. So in order to determine the value, we assume that the reaction is about to begin. It's not at begun. So that R could be taken as the initial concentration R naught. And if you substitute the value, you will get ln R naught is equal to I. And if you substitute that value in the previous equation, that is ln R is equal to minus kt plus ln R naught. This is the equation. This is one of the standard equation for the kinetics of first order, integrated rate equation for the first order reaction. And you can see an interesting factor over here. What is that? If you ask, the equation what we have written is equivalent to y is equal to mx plus c. So please understand, according to this equation, c is the intercept and m is what we call the slope of the curve. So if you plot a graph where y versus x, that is ln R versus t, you will get a graph with negative slope. It will be like this. ln R, this is time, you get a graph with negative slope, and this point is ln R naught, because in this equation it represents C, intercept, and the slope of the curve is supposed to be slope is equal to, you can take negative slope, so you will get the rate constant. And in the previous class we have discussed about the rate constant. Rate constant is the proportionality constant. And what is the significance of rate constant? As the value of k, that is small letter k, increases, the reaction will be more fast. If k value is small, that means the reaction is slow. If you take this ln R naught towards the left hand side of the equation, you can write ln R divided by R naught is equal to minus kt, or you can take ln R divided by, this equation could be again written as, if you remove the natural logarithm, R by R naught is equal to e raised to minus kt. So this is one form of the equation. You can again write the same equation as R is equal to R naught into e raised to minus kt. This is again one more version of the equation. You can have one more form for this equation, that is, take a situation, you are considering a concentration at time t1, so that the equation ln R is equal to minus kt plus ln r naught. This is the beginning fundamental equation. If you consider a situation where the concentration of the reactant is R1, so you can write minus kt1 because at T1 it happens, the initial concentration will not change. You can write like this if you consider one more situation whereas the concentration of the reactant is equal to R2, so minus kt2 plus ln R naught. And if you subtract this equation 2 from 1, so if you subtract equation 2 from 1, you will get ln R1 minus ln R2 is equal to minus kt1 minus of minus kt2. So if you simplify it, you will get ln R1 divided by R2 is equal to kt2 minus kt1. So this equation also a bit interesting. You can take in the form of y is equal to mx plus c. So this is y is equal to mx plus c. Whereas you may ask what is c over here. C could be considered as 0. So you can write like this. And if you recall that the basic equation of first order reaction, that is ln R is equal to minus kt plus ln R naught. If you wanted to simplify this equation in such a way that you are much bothered about the rate constant, then it could be written as k is equal to 1 by t ln R naught divided by R. This natural logarithm, if you have converted into the logarithm to the base of 10, you can write 2.303 divided by t log R naught by R. And one more version you have to recall related to this is, suppose you take a reactant converted to product like this, and you are considering the initial time t is equal to 0. You can take it as A moles of reactant get converted to product. So the reaction is not yet started. After some time t is equal to t1, A will react. How much is going to react? If you ask, it is X amount will get reactant, X amount of product will get produced. So if you replace R naught by A and the molar concentration of a reactant after some time T1 as A minus X, you can have an equation like this also, that is K is equal to 2.303 divided by log A by A minus X. I have introduced this equation. The reason is in many of the textbook they write like this, so you don't have to get confused. So if they are asking you to write down the integrated rate equation for the first order reaction, once you get this reaction and you can write down this equation and you can write down the version of this equation, that will do the needful. So if they ask you to derive the integrated rate equation for first order, this much is enough, and you have to plot that graph also. And here also you can plot a graph for the integrated rate equation. That is, this is the equation, the last equation. So you can write down this equation as the equation could be written as log R naught by R is equal to log R naught by R is equal to K divided by 2.303 into T. I have written like this just to compare with this is Y
is equal to m this t x plus c, and the c will be taken as 0. Then only the equation will be complete. So you will get a graph over here. With respect to the previous equation, you have got a negative slope. Here the intercept is 0 with the positive slope, and here along this axis it is t, and this axis it is log r naught divided by r, and the slope of the curve could be considered as k by 2.303. So in the previous graph you can directly get k. Here you have to get the slope, and that slope has to be divided by 2.303. And whenever they ask integrated rate equation, it is also important you need to mention what are the examples of reaction which follow first order kinetics. Very important example is, you must have heard of hydrogenation of alkene. So saturation of the oil depends on this particular reaction. So C2H6. This is first order reaction. With respect to the rate of the reaction is given as K into C2H4. Because the hydrogenation of ethene happens on the surface of the catalyst, so it's not the concentration of the hydrogen which is abundant is important. What is important is the amount of ethene is important. Another very important example for the first order kinetic is the all natural and the artificial radioactive decay of unstable nuclei take place by first order kinetics.
Next we will discuss about integrated rate equation for zero order reaction. So once you know what is the integrated rate equation for first order reaction, zero order reaction will become very easy. So let us consider a reaction. This is how you have to start. The reactant will get converted to product. So rate of the reaction could be written as dr by dt is equal to k into r raised to 0. Because for this particular reaction we already know that the molar concentration of the for the 0th power of the molar concentration of the reactant will determine the rate of the reaction. So as any quantity raised to the power of 0 is unity, you can write rate is equal to minus dr by dt is equal to k into 1. So you can simplify this equation as dr is equal to minus k dt. And when you integrate this equation on both the side, you will get on integration, you will get this equation as r is equal to minus kt plus I. As before, the I is what we call integration constant or the constant of integration. You need to find out what is the constant of integration. For that you consider at t is equal to 0, r is supposed to be r naught, and when you substitute this value in the equation, you will get r naught is equal to minus k into 0 plus I. So r naught is given as I. So you can substitute the I value in the previous equation. So you get r is equal to minus kt plus r naught. This is what the integrated rate equation for zero order reaction. So this is also in the form of equation of straight line, that is y is equal to mx plus c. So you can plot a graph that comes like this. this is time, concentration of R, you get a slope, negative slope like this, and the intercept is R0, and the slope is equal to K. Negative slope is equal to K. So variation in the concentration with respect to time for the zero order reaction is plotted over here, and the previous equation, that is this equation, could be also written, this equation also could be written as K is equal to R0 minus R divided by T. So if you write this much, that will do the needful for the examination, and you should not forget to cite one or two example, because it is little we may have to wonder how come the reaction happens, and in the reaction the role for the concentration of the reactant is nothing. It happens when the reaction is catalyzed by certain catalyst. So some certain enzymatic reactions are like that. The best example is the decomposition of ammonia on platinum catalyst at 1130 Kelvin at high pressure, N2 plus 3H2. This is the best example for zero order reaction. Here the rate low could be written as K into NH3 is equal to K. So in this reaction, the platinum metal acts as the catalyst. At high pressure, the metal surface gets saturated with gas molecules. So a further change in the reaction condition is unable to alter the amount of the ammonia on the surface of the catalyst, making rate of the reaction independent of its concentration. The thermal decomposition of HI on gold surface is another example for zero order reaction. So you can write it like this: HI gives H2 plus I2, of course both are in gaseous state, on the gold surface. This is all about the integrated rate equation for zero order reaction. So I will share the notes, or whether I share the notes or not, you need to find out the integrated rate equation for second order reaction. So that's a small task for you. You have to find out the second order integrated rate equation along with its derivation.